Welcome. In this video I'll introduce the general classification of ideal MHD instabilities. So starting from internal and external modes, what they mean, things like pressure-driven modes, so interchange and ballooning modes, and then kink instabilities. And so I'll try and give some physical picture of what these involve, how the plasma is moving, and then some small calculations to show how these apply limits to performance. So first, internal and external. These are just ways of saying whether the plasma edge is moving. So an internal instability is one where if the plasma edge is kept fixed, the plasma is still unstable. So in this case, if we have the plasma, I'll draw the plasma hot and red, so like this. This is the plasma. And then if we take the plasma and we surround it with a conducting wall, so we put a wall all around the plasma. This is a conducting, like a copper shell, for example. So this is like a conducting wall. The plasma is still unstable even if we do this. So plasma, and the boundary condition effectively is that the plasma can't move through this wall. And so if we have a perturbation displacement psi, this just says that the component of psi, which is perpendicular to the wall, so n, call this normal, is this direction here. So it's like there's the perpendicular direction to the wall, and that must be equal to 0. And then the plasma is still unstable. So even if you fix the location of the outer edge of the plasma, there's still an internal rearrangement of the plasma. So internally in the plasma, there's some instability which is driven by pressure gradients, for example, or currents, and this can still cause an instability. Conversely, an external mode is one which only happens if the plasma can move. So quite often there are modes which are say unstable, like an internal mode like this, which may become more unstable if the edge can move, but they're still called internal modes because their growth rate doesn't go to 0 when you fix the edge of the plasma. So external modes are modes which are only unstable when the plasma edge can move. And so what might happen here is you have a plasma in the middle here, and then we have a gap, a vacuum between the plasma and the wall. And so I have some gap here. Of course, this is more typical of a real experiment because usually the plasma will have some kind of distance to the wall, and then outside they have a wall. And so now the plasma can move, and so you might end up with this is still a conducting shell. But in typical experiment, this will have some resistivity. It won't be a perfect conductor, and there'll typically be some gap between the plasma and the wall. And so what can happen is that the entire plasma can move around and perhaps deform, change shape. And so you might have a plasma which kind of moves and actually moves this way and it hasn't got a kink motion. And this would be an external mode. Sometimes there are modes which are external modes, but they're stabilized by the wall. So an example is a resistive wall mode, which is stabilized by the wall, but then can become unstable if the plasma slows down, and so it has time to penetrate into a finite resistive wall. So there are kind of external modes which are very important, and they lead to, because they involve motion of the entire plasma, these can lead to disruption, so essentially destroying the whole plasma equilibrium. Whereas typically internal modes are rearranging part of the plasma inside, and so they're disruptive, but they may not cause sort of complete destruction of the plasma. Okay, then if you remember from the delta W equation, so I have the drives for instabilities, and one set of instabilities is driven by essentially a combination of the pressure gradient and the curvature kappa. And so if this is bigger than 0, then we can drive instabilities, and these are the interchange and ballooning modes. And then there's another set of instabilities which are driven by the parallel current, and these are kink instabilities. So these are not completely separate. Typically instabilities are driven by a combination of these two, and things like kink ballooning or peeling ballooning modes are combinations of these drives. But it's useful to try and classify them or try and think about them in terms of these drives separately to start with. And so the pressure-driven ones, so this grad P, this equilibrium pressure gradient and curvature, so this is driven unstable if you have a magnetic field like this, so that curvature is down like that, and then if we have the gradient of pressure in the same direction, so this means if you have high pressure on the inside and low pressure on the outside. And this happens, for example, in a Z pinch. We have magnetic field curved around like this. So this is magnetic field, and so the curvature vector is always towards the middle, and so is the pressure. So the pressure gradient is also always towards the center of the plasma, because you have a high pressure in the middle and low pressure on the outside. And so this is unstable. Conversely, we can stabilize it if we can either essentially flip the direction of this curvature. So if you have a high pressure on the inside at the top here and a low pressure on the outside on the bottom, and one configuration that does this is the magnetic cusp. And so here we produce a magnetic field typically using 4, or as many as you like, but for example with 4 conductors. So you have conductors like this in some kind of arrangement like this. I've drawn them alternating currents. So here we have a current going into the page, and this makes a magnetic field going around like this. So here's a magnetic field, and then here this current here produces a field going like this, and then here we have another current going to the page. And here coming out of the page again. And so what we end up with is a configuration where there's the smallest magnetic field in the middle. It's the minimum in magnetic field, because the field from all these components cancel out, so we have 0 magnetic field in the middle. And we have the curvature of the magnetic field lines, so which our curvature is doing, let's see if I pick this colour for curvature. So curvature is now always out this way, because it's the direction the field line is bending in. So this is the curvature. But the gradient of pressure, so we're trying to get high pressure in the middle, so the pressure gradient is always inwards. And so this is a stable configuration. So we always have that grad P dot kappa is always less than 0, and so this is stable. Unfortunately, these configurations have terrible particle confinement, because there's magnetic field lines going straight through the middle, and so typically field lines, particles will escape along the field lines through the gaps here. But this basic configuration is used in combination with magnetic mirrors, for example. These are called Ioffe bars. These are used to stabilize tandem mirrors. So this idea of having a minimum in magnetic field in the middle as what stabilizes interchange or pressure-driven modes. And so this is the opposite of this. So in a Z pinch, the magnetic field is decreasing as you go radially outwards, and so as the plasma expands, the magnetic field drops, and so the magnetic pressure that's confining it also drops. Whereas in the magnetic cusp, if the plasma expands, the field increases, and so it pushes back the plasma to its original position. And so in these kind of configurations, there are instabilities. In the Z pinch, for example, there are instabilities which are essentially constant along field lines, and instabilities which are constant along field lines are often called interchange modes. So these are pressure-driven instabilities where the parallel K, so the variation along the field lines, so this is B dot K, is roughly 0. So what this means is that the gradients along field lines, so B dot grad of anything any like perturbation, for example, is roughly equal to 0. And these are analogous to the Rayleigh-Taylor instability in fluids. So the idea is in a Rayleigh-Taylor instability you have say two fluids, one on top of the other, and we have a heavy fluid and a light fluid on the bottom, and gravity is downwards. So water above oil, for example. This is unstable because it's energetically favourable to interchange these two. So the energetically it's a lower energy state to move the heavy fluid down and the light fluid up, and so you get these instabilities where there's sort of bubbles rising and the heavy fluid is falling. A similar thing happens in plasmas, where effectively the curvature is playing the role of gravity, and here the pressure gradient is kind of playing the role of the different densities here. And so they have the pressure gradients, the curvature, and so you end up with a case where it's energetically favourable to swap two flux surfaces. And so what happens is that one set of field lines moves up, one set of field lines moves down, and you end up with this similar kind of bubbles and heavy parts falling. So I'd have let's see, if you have a set of field lines like this, and a set of field lines above them, one different colour. It becomes energetically favourable to swap these two field lines, or these two flux surfaces, and so what can happen is that these surfaces move down, and the black surfaces move up, and you end up with essentially a wave where you have kind of rising and falling bubbles, but the wave is constant along the field lines. So if I draw what it looks like over here, so it's also the black one's moving up and the red one's moving down, and so it's that the entire field line is moving down together, and these field lines are all moving up, and so there's no variation along the field line. Okay, so in a real in most 3D toroidal machines like tokamaks and stellarators and stabilized mirrors, the field lines are moving between regions of good and bad curvature. So so these leads to ballooning modes. So these are very similar to interchange modes, except that k parallel is not equal to 0. And this happens because in these machines, if you look from the top of a tokamak, for example, you have the plasma as a kind of donut, and access the machine here. The field is mainly around this direction, and so the curvature vector is mostly inwards. So kappa is always inwards like this. But now the highest pressure region is in the middle here, so in the core of the plasma. And so the gradient of the pressure goes inwards like this and this way. So we have low pressure on the very inside, low pressure on the very outside, and then highest pressure in the core of the plasma. And so in the outside edge of the plasma, here where you have grad P is inwards and curvature is inwards, this is the bad curvature side. So it's where grad P dot kappa is greater than 0. And on the inside here we have grad P is outwards and curvature is inwards, and so here we have good curvature side. So here we have grad P dot kappa is less than 0. And field lines in this configuration are moving between the two. So we have field lines which start, say on the inboard side here, and they're spiraling around the machine, and the field line will move. So around the machine from the good curved side on the inside, around the outside, then it'll spiral around and then back to the inside, and spiral around here, and then back. So a field line is moving from good to bad curvature. And so if you plot along the field line, this kind of distance along the field line, what will happen is we have a good curvature here. So this might be where this is point A, say where it's here on the inside. And then it spirals around out to bad curvature region. And this might be this point over here. Point B. This is point A over here, point B over here. And then it spirals round, back around the machine onto the inside, then back to the inside. And so what will happen is that the plasma can be energetically favourable for the plasma to move outwards here. So the pressure drive is making the plasma unstable in this region here. But any motion of the plasma in this region will be stabilising. And so what happens is that there's a balance between the stabilising effect of the good curvature and the destabilising effect of the bad curvature. And typically there's a limit to the pressure gradient, and if that limit is exceeded, then it's favourable for the plasma to balloon outwards. And so what happens is the plasma moves outwards on the bad curvature side, but not much on the inside. And the field line is now bent. So we have a bending of the field lines. That means in the delta W equation, there's a term which is like delta B perpendicular squared, which is the energy going into this bending. And if that energy is less than the energy that's gained by moving out on the bad curvature side, then the plasma can become unstable. And so what you see in experiments is instabilities which occur on the outside of the tokamak. So if you have a torus like this, so we have down the middle, you have good curvature on this side and bad curvature on the outside. And so what we'll see typically is instabilities which appear on the outside of the machine. And these are kind of spirals. So if you follow this one, for example, it goes to the inside, and then you won't see much on, there's not much perturbation on the inside, but there's a large perturbation on the outside. And so these structures appear on the outside in the bad curvature region. And these are important for things like edge localized modes. So for example, which are called elms, which lead to eruptions on the outside of the tokamak, which lead to big heat loads on surfaces. So these are ballooning modes. And then lastly, I want to come on to kink instabilities. So there are two main types of kink instabilities. So the first is internal kinks, and these are relatively few in tokamaks, but they mainly occur around the Q=1 surface. And so what happens is, if you draw the edge of the plasma like this, so we have a toroidal plasma again with the axis down here. You have nested flux surfaces on the inside, and what will happen is that these flux surfaces on the inside will begin to kink, to move. So for example, these flux surfaces might move down, so this is displaced downwards, or these ones move up. And so these inner surfaces are like tubes inside here. What's happening is that these kink and these move as this is being displaced upwards. And if there's too much current inside the plasma, then this can cause this inner surface to kink and eventually to become unstable. And these are associated with a drop in the safety factor. So if the safety factor Q if that drops below 1, then this can occur. Remember, safety factor is the number of times a field line goes around toroidally this way compared to times it goes around this way. And so if there's a Q=1 surface, you can take the core of the plasma here, and this will form like a ring. I'll try to draw this around here. So this whole surface is forming a ring. So this would be a Q=1 surface, so it's going around once toroidally and going around once poloidally as well. So this would be a Q=1 surface. And it's the whole inside of the plasma is tilting and twisting. And these are seen experimentally, associated with Q around 1. What's seen is if you look at soft X-ray, for example, signals coming from near the core of the plasma, what happens is over time, this is a soft X-ray, so this is essentially measuring the temperature of the plasma, at least a proxy for the temperature. What will happen is that it'll go up, and then you'll see a crash, and then this will typically repeat sort of quasi-periodically. These are called sawteeth, or sawtooth oscillation. And if you look slightly outside, so this would be the core region. If you look slightly outside the core, again against time, you'll see the opposite thing, that the temperature will gradually drop, and then you see a spike. And so every time there's a sawtooth, what's happening is that heat is being thrown out of the core and then arriving slightly outside the core. And so these periodic oscillations are essentially caused by current, which is diffusing into the plasma, building up in the core, so the core safety factor is dropping. And when the safety factor drops a bit below 1, these are triggered, and you end up with another instability, and then the whole process starts again. So it builds up, crashes. Okay, so the last type of instability I want to discuss is the external kink, and this is quite a dangerous instability for tokamak plasmas, because it involves the entire edge of the plasma moving, and so if the whole edge moves, it can then hit the inside wall of the tokamak, so causing a disruption. And so in Z-pinch, for example, this happens when you have too much current. The whole plasma deforms. So in a screw pinch, or a tokamak, and so the entire plasma kind of twists and deforms. So you might have the whole plasma edge kind of twisting around like this. So if this is like the whole plasma twists. And this can happen when you have too much current in the entire plasma. So, the strongest limit on tokamaks is, for example, you have Q, the safety factor at the edge of the plasma, must be less than 1. If it's bigger than 1, then the entire plasma can become unstable, and this is the Krushkov-Shafarnov limit. And so Q, the safety factor, this is approximately given by this expression for circular cross-section large aspect ratio machine, so where the major radius is much bigger than the minor radius. This is given by the toroidal field divided by the poloidal field, and then times by the minor radius A and the major radius R. And so here is the minor radius, R is the major radius. And we want this to be less than 1 this to be bigger than 1 for stability, and so if this is less than 1, then it becomes unstable. And then what we do for a circular cross-section tokamak, so if this is like the cross-section, we have like a major radius R, a minor radius A. The magnetic fields you can work out by taking a surface around here. So the integral of B dot dl, so B in this case ends up being B theta, is just the plasma current times mu naught, so mu naught times IP for the plasma current. Then for circular cross-section, this is approximately 2 pi A times the poloidal field. And so you can use this to substitute into here. So this is for stable. Okay, so we substitute this expression for B theta into here, and we just get that. So we can rearrange this into an expression for the plasma current, and so you must have that the plasma current must be less than, so this is IP, the plasma current, and so for eta, for example, so e.g. eta, so here major radius is roughly 6.2 meters. Minor radius is about 2 meters. Toroidal field is around 5.3 Tesla. And so the whole thing, this gives the plasma current limit is roughly 17 megaamp. So that must be the limit. So if for stable, you notice that in each of the pan is roughly 15 megaamp for steady state, which is getting uncomfortably close to this limit. What makes a big difference is the elongation of the plasma. So if you have an elongated, so a stretched plasma, the plasma current limit goes up quite considerably. So I'll just note here that this is a limit for circular cross section, and for an elongated plasma this can be much bigger. But this does provide at least an upper limit on the plasma current that can be carried.